Our next speaker probably doesn't need any introduction. Denis Peach, also linked to Imperial College and chief scientist for so many years at British Geological Survey. And that last question is a good transition. It is this question of how do you go from just characterizing to actually applying some models in terms of decision making. And this retrospective, I think, will be very helpful. Thanks, Denis.
Thanks. So, towards a vision of integrated models for decision making, we've come a long way in surface water groundwater interaction over the past, well, I suppose over Howard's career and my career, we certainly have. But we're sort of a long way from employing models that are actually used for decision making by policymakers, really. And there are a variety of reasons for that, which I'm not particularly going to go into. What I do think is that what's happened in my life is that I want to use a couple of examples, which I spoke about last night, to illustrate some of the complexity of groundwater surface water interactions before moving on to what we have been doing at BGS in the last few years and pointing perhaps to what should happen in the future. So I made this journey with Howard. I suppose we started in Oman, looking at Wadi gravels. Then we moved to Ireland, looking at flooding in the Gort-Ardrachan area, which was karstic, and then we started to develop integrated models to assist planning in water resources in the Thames, which is where we're most advanced, really, and then what we're going to do in the future. So, yeah, well, here we are. This is, is that the pointer? Yeah, that's a Wadi. That's Wadi Ghulagi, in fact. This is where it is. That's the Jebel Akhdar, and this is Oman, Sultanate of Oman. It's pretty dry there, and this is the Ghulagi. Can't make it work, actually. This is the Ghulagi catchment up here on the line. Now, what we thought when we arrived there was that, this Wadi here. Is there another one of these? There's a big one, yeah. Yeah, we thought that, this would just be filled with gravels, unconsolidated gravels. And in fact, there's some outcrop here of gravels. And they're not unconsolidated, as you can see there. They're cemented. And in fact, it turned out that there's some more cemented gravels. They're in a different place, but they're clearly cemented, because otherwise they'd be falling on top of that guy there. And they're not. I didn't think that photograph was there, actually. I'll come to that at the end. But this is our sort of conceptual model of what was going on. So the groundwater system that we were trying to build a dam above to allow Wadi floods to infiltrate to was not simple at all. In fact, it was quite complicated. So we have all these cemented gravels, which, it was like drilling through concrete, actually. I mean, they're not very permeable at all, hardly fractured at all. But there were fractures at the bottom. There were fractures at the bottom because in here you've got ophiolite. This is dragged up from the mantle, if you know what that is. I mean, from very deep down, because that's it's the site of two plates crashing into each other, Oman, really. And pH is in here, in the waters in here, and there is water, but not very much, are about 9, between 9 and 11. So it's not very pleasant. You wouldn't want to drink it. And this causes the calcium carbonate to come out of solution in the recharge water, and it gets deposited. So, but there are some uncemented gravels. So we built a groundwater model to represent this system. But of course, we had to represent the whole system. So this was Howard's bit, basically. That was my bit. So he built a rainfall generator, and you heard yesterday from Richard Chandler about rainfall generation. This was pre-Richard Chandler. He comes in Ireland, in fact. And then there are 3 three models of the plains, if you like, and the Wadi bed, and a groundwater model beneath. Now, we weren't hugely successful at this, but we were successful in calibrating the recharge through these systems by looking at water levels in the groundwater model, which is very odd because most of the time with groundwater models, we calibrate them looking at flows in the surface water. Here, it's very difficult to measure flows. I mean, you can put in a flow gauge and it gets washed away by the flood. So it's actually quite difficult to measure them. And so we decided to try and look at the recharge and calibrate these models using the groundwater model and the rise in groundwater levels after a flood event. Fortunately, we did have a flood event while we were doing this work, otherwise it would have been a bit of a problem, I think. But so that was one of the first sort of, it's a complicated situation which you need to try to understand in order to understand the complete water cycle, I suppose. Now, next, we move on to, I need to have a drink, to Ireland, and I asked Howard, again, to help me out with the hydrology in the Gort-Ardrachan flooding problem, which happened in the early mid-90s. And you see here the flooded situation. It's, this is the sort of catchment, if you like. It's a bit difficult to define the catchment because the rivers, as you can see, which come off this Devonian sandstone here, just disappear because this is Carboniferous limestone. There's a major spring, massive spring at Kinvara, which runs straight into the sea. We did try and gauge that with, or some of my staff tried to gauge that with boats and impeller flow meters and all sorts of things, but it's quite difficult. And you've got sort of disappearing streams. You've got lakes dry in the summer called turloughs. And what happened in these high rainfall periods was that the turloughs overtopped. This is what the limestone looks like. This is what one of the turloughs looked like when it got water in it, and sometimes it didn't have water in it. This was the actual extent of the problem. Lots of people, I think 19 families were flooded out and had to leave their homes permanently, and their homes were knocked down, in fact. This is an area called Blackrock, and this is Loch. This is normally, in the summer, dry. And if we look a bit closer at the situation here, this is Blackrock here. After the water level's gone down, these are the sorts of swallow holes and springs that you get in the limestone. And that's a guy called John Lloyd, actually, who's a very good hydrogeologist. And this is a 24-hour period in Blackrock Turlough, and it's flowed into by one of the streams, or three streams coming off the Devonian sandstone. And as you can see, in 24 hours, and this is more or less the same place the photographs are taken from, it fills up. And this is a big lake after 24 hours. In fact, we were monitoring this, or at least we had a logger in the bottom and a transducer, and it came up so quickly, my staff had to come out and climb up trees to raise the thing up trees because it would have got flooded out. So that's the sort of problem that we were dealing with. Now, we modeled it using an equivalent pipe network. That's the pipe network. We had a rainfall runoff model here on the Devonian sandstone. And, of course, we had the rainfall generated by Richard at Chandler, and you heard about that the other day. And then we had to calibrate it. How the hell are we going to calibrate it? So, as I've just said, we looked at these turloughs, and we put loggers in several of typical turloughs, and we monitored the rise and fall in the water level. It didn't actually flood. I mean, the turloughs got full of water, but they didn't overtop during the period that we were doing the study. And it was only a two-year study, but it was a very expensive study at the time. And and we put in a lot of infrastructure. We drilled a lot of boreholes. We did a lot of investigation to try and characterize this, this pipe network, which we did. And we remapped the geology because there wasn't a geological map. And we came up with this sort of conceptual model. There are two types of limestone, one of which has got caves in it and the other one hasn't, basically. One of them is fractured, and we were able to map to some extent the cave systems and put in our pipe network. So, I mean, all I'm trying to indicate here, and this is, I mean, this is part of the pipe network, and this is the equivalent the pipe network, and this is the actual situation, if you like, where swallow holes, and so we put in these levels where they overtopped and so forth. And we were able to do that, but all I'm trying to indicate is that this is pretty complicated. It's not easy to do this at all. But we did manage to do it. There again, that's the modelling the real thing. And you've got these tanks, if you like, overflow weirs and so forth. This is just the pipe network. And these are some results. So we didn't do too badly. We had a calibration period and a validation period. We could only run the model for about 6 months, in fact. But we made progress. I mean, huge progress, really. And all of this sort of puts me in mind of what we need to do in terms of integrated modeling. Those are integrated models. They were one-off models built to address a particular problem. So if we move on to, say, the Thames Basin, which is here, you've just seen, I think that's the rainfall in, you know, so we've got quite a lot of rainfall in here. But that's the Thames Basin in red there, here, again, and this is over the top of the geology, so this green stuff is the chalk. Okay, up here, in this area, we've got the Cotswold limestones, they're Jurassic limestones. In between them, we've got thick clays. But they're all provided, both these aquifers are providing base flow to the River Thames. The River Thames is about 10,000 square kilometres. This area has a population of about 16 million, and it's obviously important. I mean, if London runs out of water down here, it may not matter if Brexit happens, as we think, because all the financial services may have gone to Frankfurt by then. But hopefully that won't happen. But, you know, one of the questions that has always been in my mind is when will London run out of water? It's all supplied from the Thames catchment, either from the north in the chalk here or from the river itself. And, of course, the river in the summer is base flow. It's groundwater. And why does it matter to sort of model the whole thing? Well, you know, here we've got some droughts, and you can see that rainfall, in this one, for instance, you can see that it's raining much more. There's much more rainfall on the limestones up here than there is on the chalk. That's 76 drought, and it's just a bad drought. It's just really bad. So it does matter where you are. It's a big enough basin for the rainfall to be different over here to what it is over here. So you've got to try and look at that, otherwise it doesn't work. Now, how are we going to do that? Well, we know something. We know a lot about this because of Loch. This is the chalk here. We know a bit about the Cotswold limestones. We've run, you know, quite a lot of master's projects and the odd PhD, well, mostly master's projects actually, and done quite a bit of work down here. Along the Thames, along here, there's a load of gravels. I haven't shown them on this plan. So there's a load of gravels. Do they act as a headwater storage, if you like, for the? So we don't know enough about this to build a sort of distributed numerical model in the same way that we have for the chalk, but we know enough to have built a lump parameter model, semi-distributed. In other words, I think we've got about 11 areas in this area here, and we can calibrate that to groundwater levels and flows, of course, in the river, because the Thames is obviously monitored. So we've got two different situations in terms of data, two different situations in terms of, you know, this is a major aquifer, and this is major aquifer as well. Now so what we've done, and I've got no results to show you at the moment on this, but this is what we've done. So we've got this semi-distributed model here, groundwater model. We've got a fully distributed, it's not mod flow, but it's a bit like it in a way. It's much better than mod flow, but I would say that, wouldn't I? And we've got a recharge model over the top, and they're all connected to a river model. And you can link into this, systems models. So you can start pumping things, putting sewage effluent into the Thames and this sort of thing because you're abstracting from the Thames at one point, pumping it up the catchment, and it goes back in from, say, Oxford or wherever. So you can start to operate this as a complete system. Surface water, groundwater, recharge, rainfall, and obviously you can, if you want, and if you've got the information, the data at these sort of scales, you can put in climate change and run scenarios and so forth. And that's really more or less what I wanted to say. In other words, you've got simplified models, you can connect them to complicated models where you've got the data and the information and the understanding, and you can put recharge on these models, as we have done here, and in the future, you can link them to ecological models, water quality models, and this is already happening, and population models, socioeconomic models, infrastructure models. And that is basically where we have to go. That's where we have to go if we're going to answer the questions of the grand challenges of population, urban growth, and climate change. And that's really all I wanted to say, except that these are some photographs in Oman. This was the team. There's himself. There's himself filming me. He hasn't actually got it. Filming me digging a hole. We dug a hole and then poured water into it to see if we could see whether it disappeared or not. That's the sort of level of science that was happening out in Oman in those days. And that's all I have to say. Thank you very much.
Question for Denis.
There's a load of blank faces.
One up there somewhere.
Oh, well, that's good.
Well, I'll ask one.
Oh, you'll ask one. Yeah.
So many of the couple surface water, groundwater models, we calibrate them to some downstream data set. But we seem to always avoid the issue of can we do a better job at actually getting, in my view, the biggest number of concern is recharge.
Yes, I mean, I think recharge is my problem is with, you have to look at who's doing the modelling. Recharge is sometimes used in inappropriate ways to fiddle the model. So I don't really like that. What I like to do is I like to understand how it works, how the aquifer works, or the aquifers, you know, and with this, you see, because we've got flows on the Thames, we can calibrate to flows on the Thames. We can calibrate, if you like, to groundwater levels. And of course, you can make any groundwater model match any set of groundwater levels. So you've got to be a bit circumspect about it. But I think that the recharge is the key, and it's always the key. And Howard and I are now working in Chile, and it's an even bigger key in Chile because there isn't much of it. I mean, there's the rainfall we're talking about in some of these areas is only 150, 140, 120 millimeters per year. So, you know, theoretically it all disappears but it doesn't, it goes in. So you have to come up with some conceptual understanding of how it works, and you have to have data. So you have to know the infiltration capacity of the soil and so forth. You have to understand the recharge process. Adrian talked about the recharge processes and the fact that in the chalk you've got this piston flow because you've got this little reservoir. But on the other hand, Howard and I, when we took Nicholas into the field, had an enormous storm and watched surface runoff on the chalk. I'd never seen it before, actually. So it's complicated. I suppose that's not a very good answer, is it? It's complicated. But there you go. Okay.